All right, good morning, everybody. Can you hear me and can you see the board clearly?
Yep.
Okay, cool. So, some announcements. I'll be finished with the chapter today. So the chapter 23 homework is due Sunday night. I'm hoping that you will show up tomorrow night with your questions on the homework. Okay. Remember, I have hours from 5 till 6:30, and if I have time in lab on Friday, you can always interrupt and ask me if I have if I'm able to ask questions on the homework on Friday. You can always ask. Okay. I'm going to try to go as quickly as I can through the lab on Friday. Okay. On the worksheet, the electric field worksheet is due on the 17th. That's basically going to be an exercise for you to carry through this. Basically, you're going to go through the steps in calculating an electric field for a continuous charge distribution. I did an example the other day. I'm going to do 2 more today. If you go on Canvas, if you look at the modules, I have another example. So you want to look at the module for this unit for chapter 23. There's a bunch of videos on the material from chapter 23. One of them is me solving a problem where I calculate the electric field due to a disk along the axis of the disk. Okay. The properties of charge lab. I got the lab from you guys. The building the apparatus lab. I got that on Monday, and my goal is to grade the first lab and this lab this week. I graded 3/4 of the first lab, the review worksheet, and then we had the exam, and so I kind of stopped grading it. So I'll probably grade those over the next 2 days, and then you have the properties of charge one due on the 25th. Okay, so as you're doing that lab, please, if you have any questions, don't hesitate to ask. Remember that for the properties of charge lab, you can use you can have lab partners, but if you're using lab partners, I would like for you to be working together on them. And if you can wear a mask if you're concerned about transmitting the COVID. If you want to do that, okay, and that's up to you. But I'm letting you do that if you want to. Otherwise, you'll do it as an individual lab, okay. And that's due on the 25th. And I'll probably send another email about the lab. Get started early on this lab. This is not going to be like the building the apparatus lab where some people kind of did it towards the closer to the deadline. You can't do this at on the 25th. It's going to be pretty tough for you to complete the lab if you do it on the 25th. Because you got to practice, you got to play around with the equipment, try to make things work. Then you got to decide for like part 1, which one do you want to video and explain. So you have to do a little bit of thinking ahead of time. If you do everything at the last minute, this is not going to go well, okay? And you're going to spend probably way longer than you would have wanted to. Okay, just as a warning, all right? Okay, so today I want to do a couple more examples on calculating electric fields, and then I want to talk about the kinematics and dynamics of charged particles and static electric fields. Mainly electric fields that are uniform, okay? That's really what I'm going to focus on. And you have a homework problem on this. Well, actually, you have a couple of them on this topic where the field's uniform. And then I want to introduce field lines. That's chapter 24. And then Monday we'll talk about Gauss's law, okay? So the other day, I was calculating the electric field due to some sort of charge distribution. And I said, if you have some arbitrary charge distribution, a continuous distribution of charges, meaning that the number of charges that makes up this object is not countable, okay? I want to determine the field at this point P. This is a location in space. And I said that in order for you to be able to calculate the electric field here, I have to break up this object into pieces small enough so that the contribution of the electric field due to this object over that entire piece is the same. Okay? Question? And so I need to know what that dq is. I need to know the unit vector that goes from that source to the point at which I'm calculating the field. And I also need to know the length of the vector that goes from the source to the point P. That's what R is. And so you can make, you can kind of make this like, your origin could be over here, I guess, or you can make this your origin, but for that particular object. Are we okay with that? Okay, and then we say, well, let's write down the expression for dE. The electric field due to that little dq. I have to do this process for every single dq that makes up this object, and then I have to sum them up. Well, if this is infinitesimally small, that sum becomes an integral. And so then the electric field is the integral of k dq over r squared r hat, where the integration is over the object, is over the charge distribution, whether it's a length, an area, or a volume. So in order for you to be able to do these calculations, one, you have to determine, well, you have to choose a coordinate system. Okay. You have to write an expression, a mathematical expression for your dq. You have to break up your object into pieces small enough such that the electric field is the same. The electric field at this point is the same over that entire object. Okay. Then you got to determine the length of this vector, and then you got to square it, and then you got to determine your r hat, your unit vector r hat. Then you put it all together into this equation, and you integrate it. That's the process. And the way I wrote the worksheet, the worksheet is really two different problems, but I broke it up into parts because I want you to follow the process. So I broke it up into the process you should follow in solving these problems. Okay, if you look at the worksheet, I broke it up into the process you should be using to solve these kind of problems. It's just the process you have to learn. Okay, however, the hard part is really the math and understanding how to set up this dq, how to set up the r hat and the r. That's the hard part of those problems. The integration, to me, this is a physics class, and you guys are probably really good at doing integrals. You have that information. I haven't done those complicated integrals you do in Math 31 for many years. You guys can probably do them much more quickly than I can. But I'm not as interested in the integration techniques. I'm interested in how you set up the integral, because that's going to allow you to calculate E. Okay? A lot of the integrals will be easy. Some of them will be challenging, and the ones that are really difficult, like on an exam, if you have a really difficult integral, I'll actually give you a list of integrals on the exam, and you can find the right one, and it'll give you the value. Okay? Just don't tell your calculus teacher that I'm having you do that. All right? I'm more interested in you being able to set it up. I'm interested in the process, because if you can set up the integral, you can do any problem. Okay. Questions on this? Now, one important item is the r hat. The r hat can be very complicated. It can be hard to write. However, a lot of these problems have symmetry. And because of that, because of the symmetry, some of the components of our hat will cancel when you do the integration. So you can use a little bit of physical intuition to only include the components of our hat that will not be zero after you integrate. And I'm going to show you that in the first example I'm doing today. Okay, so let's go ahead and do an example. And I forgot to turn on my keyboard. Sorry. So this first example, I have a ring of charge. And its uniform charge density. I want to calculate the electric field along the axis of the ring, but out of the plane of the ring. So let me try to draw that. It's easier to draw it for me in PowerPoint, but I'm going to try to draw it on the board. Okay. Let me draw my coordinate system. And let's try to draw this ring. Okay, so there's the ring, best I can draw it. I want to calculate the electric field at this point P, which is a distance Z above the XY plane. The radius of this ring we'll call A. Okay, we'll call the radius of the ring A. And what I want to do is break up this ring into pieces small enough so that the field is uniform over that. The field at this point is uniform over that little piece. So I'm going to break it up into an arc length. Okay, or I can draw it here. I'm going to break it up into arc lengths. This angle we'll call d theta, and then the radius is A. Okay, so I'm going to break this up into this smaller piece. I want to calculate the electric field into this thing. I want to remind you about a problem we did the other day. We had a uniformly charged ring, and I asked about the field at the center. What was the answer? What was the electric? It was 0. Okay, just remember, now what we're doing is we're going out of the plane. So in the plane, the field was 0. So I'm going to expect then that the components in the plane are going to be 0, and my field is only going to point in the z direction based on this argument. But it's true that each piece that I have of this ring, the electric field is going to point in a different direction. And the reason why is because, let's say if this is positively charged, for this piece, the electric field points towards the center, or actually towards this guy. The x component points this way, the x and y components point this way. And for this piece, the z component is the same, but the other components, the x and y components, point that way. So these two arrows point in different directions. Okay, so the x and y components do change, and that's why I'm breaking this up into little tiny pieces. But although I know that when I integrate around the ring, the x and y components will cancel. Okay. I want to write down my dq. For this little piece. of length ds. So this is going to be the charge per unit length times our ds. Right? If I have a rod that's 1 kilogram and I want to know the length, let's say the rod's 1 foot long, and I want to know what is the mass of a piece that's 1 inch, then I take 1 kilogram divided by 12 times 1 inch. And that's going to give me the mass. It'll be 1/12 of a kilogram. So I'm doing the same thing here. The charge per unit length times the length of the element gives me the amount of charge in this piece. In one dimension, we denote the charge per unit length as lambda. ds is an arc length. What's the equation for arc length? Anybody remember the equation for arc length? I guess anybody's saying it, I can't hear them. Okay, so arc length, delta S, is radius times delta theta. And so ds, the infinitesimal version, is r d theta. And so the ds here, our radius we called a. Okay, our radius we called a in our problem. So this is lambda a d theta. Okay? Now, what's the charge per unit length? If the charge is uniformly distributed around the ring and the total charge is q, isn't it true then the charge per unit length is q over whatever the length is? What is the length of that circle? Well, it's a circumference. And so I'm going to write this as q over 2 pi a times a d theta. And then I cancel out my a's. And if you notice, if I integrate my dq from 0 to 2 pi, I get the total charge q. Okay, so I have dq is q over 2 pi d theta. Now what about r squared? Oops. The unit vector r, the vector r is the vector that goes from, I don't have enough colors, let me try brown. That doesn't work. The unit vector that goes from, the vector that goes from here to here. That's r. And its length is the same all the way around, because this distance is the same all the way around, and then this distance from the center of the ring to the ring itself is always the same all the way around. So really, this distance I can get from the Pythagorean theorem. It's this squared plus this squared, and then take the square root. So the magnitude of that vector is this. And r squared is that. So now I have 2 out of 3 items done. I've done this, and I've done this. The last item is to figure out r hat. It's the unit vector. It really is the direction of this vector. Okay? All I need is the direction of that vector, which would be the vector r, divided by its length. So the unit vector r is a unit vector. Let's call this angle alpha. I want to know the unit vector that goes from here to here. This is going to have a k hat component, it's going to have an I hat component, and it's going to have a j hat component. This is going to be hard to write because this has three components. We usually don't write in physics. We haven't got to the point where we're writing vectors in terms of three components. So this would be hard. However, we know that the electric field at the center of that circle is 0. And whether you're at the center or along the axis, the x and y components of that field have to be 0. So these two terms of the unit vector I don't care about. I'm only going to care about the component of the unit vector that's in the z direction. Okay? I'm only going to care about the component of the unit vector that's in the z direction. So only this one. And so that's going to basically be z over z squared plus a squared to the 1/2, which is basically the cosine of this angle. And the other terms I don't care about because those components will cancel. So now I have everything I need to be able to calculate the electric field due to this ring at this point up here. So all I got to do is write my dE. I have my dQ. And now I got to put it all together. Okay. So let's put it all together. dE is K. dQ, which is going to be Q over 2 pi d theta over r squared then our r hat, and it's in the k hat direction.
Professor?
Yeah.
I was wondering, how did you get the cosine alpha again?
The cosine alpha, well, it's
Yeah.
the z component of this unit vector is z over the length, right? The z component of this vector is going to be z k hat. And then if you divide by the magnitude of the vector is this. So I'm going to get z over that. And that's the cosine of this angle.
Oh, okay, gotcha.
Okay. So I can replace this cosine of alpha with z over the square root of z squared plus a squared. And this looks like an intimidating integral we're going to have to deal with, but it's not. Let me simplify that a little bit. Sorry, I don't have enough board space. And when I integrate, this is actually an easy integral because I'm integrating d theta from 0 to 2 pi. Because I got to integrate over the entire ring. That integral is really the integral of d theta from 0 to 2 pi, which just gives you 2 pi. So the integral is easy. The setting it up is the hard part. So,
could I ask a question about that cosine alpha?
yeah.
Why would we have to write it out if you converted it back to what r hat is already?
Why did I have to convert it?
No. I'm saying, like, why would you want to make it cosine alpha if in the integral you're going to use the other form of it?
Just to show you what it looks like, what it is, from the triangle, that's all.
Okay, that's why I was confused. Thank you.
It just, because really the triangle that we have, this is A, this is Z. And really this has X and Y components because this is an X and Y plane, but this is alpha. So r hat is basically this is not correct. Okay, this is not correct. There's a bunch of other stuff in there. And so this term is just the cosine of alpha. So I can relate it to this right triangle. Okay, I shouldn't even write it that way. It's more complicated than this, that term. Okay?
All right.
So anyway, when I perform the integral, I have an easy integral to do. And what I get is that the electric field is equal to K Q over Z squared plus A squared to 3/2. And I forgot a Z. And I forgot a Z here. That's it. I'm done. So the integral was easy. Okay? It's the setup of the integral that's hard. Once you learn how to set up the integral, then these problems are generally straightforward. But in order for you to get good at this, you have to do a lot of practice. Okay? So, just to see if this equation is correct, if you let z go to 0, what do you get? Well, you get 0, which is what we talked about the other day. Finding the field at the center of the circle is 0. This equation agrees with that. What if you're really far away? What if you're really far away from the ring? What if z is really big? If z is really big, what does the ring look like? If you're really far away from the ring, what does it look like?
It looks smaller. Like a dot?
It looks like a dot. It looks like a point particle, right? And so if you're really far away, then the field should look like the field due to a point particle. Isn't that true? If z is big, then this term I can ignore. I get E is K Q Z over Z squared to 3/2 k hat. And this comes to k q over z squared k hat, which is the field due to a point charge. Can you guys see that okay? I'm too far away from the computer screen, so it's hard for me to see. Okay. And so that's the field when you're really far away. And in degrees, it looks like a point charge, and it acts like the field due to a point charge. Now, the next question is, what if my lambda was not uniform? What if my lambda depended on theta, for example? Well, if my lambda depended on theta, then my integral would look like this. I would actually put this in my integral. I would write this inside my integral. So it would look like this. Then the lambda, I could not pull out of the integral. See, Q here, the charge density was uniform, so I can actually pull this out of the integral. But if this depends on theta, I can't do that. This becomes part of the theta integral. Okay? In the homework, you have, I think it's problem 9, you have a problem on calculating your DQs for various charge distributions so that you get to understand how to calculate your DQs. So there's a whole problem in the chapter 23 homework I created so that you can learn how to calculate your DQs. And that particular problem relates to pretty much all the problems we will be doing in this unit. So if you can understand how to do that problem, you should be able to understand how to set up your DQ for these problems in this unit. Okay, so make sure you understand that problem. That one's very important. And you might have had a problem like that in Physics 205. I don't know, I mean, it depends. We used to give a worksheet it was called a distributed mass worksheet in Physics 205. And I don't know if you did it in that class or not. Okay, so anyway, I have a video of taking that ring, the field due to that ring, and calculating the field due to a disk. What if you have a two-dimensional object like a disk? And you want to calculate the electric field, let's say at the tip of this marker along the axis of the disk. Okay? Then what? Actually, writing your r squared and r hat are not going to change. Okay, the r squared and the r hat are not going to change much. What's going to change is your DQ. How am I going to break this object up into a lot of pieces, or into a piece such that the electric field over that piece at this point is the same? Well, I can say, oh, let me break it up into a square. I can do that. The square has dimensions dx and dy. I can do that. The only problem is then you're stuck doing a two-dimensional integral. You're stuck doing a double integral. We're not supposed to know double integrals in this course. Okay. So I have to give you problems that have sufficient symmetry that you can write it as a single integral. If the charge density is uniform, or it only depends on r, you will see that if I take this disk and break it up into a bunch of rings of thickness dr and radius r, that the field at this point anywhere along this ring is the same. the z component of the field at this point, anywhere on that ring, is the same value. So I can break up that disk into a bunch of rings, a lot of rings. Like imagine you take an old tree, you saw the tree, and you see all the rings in the tree, and you think of each of the rings in the tree as one of these rings. And so my dq is going to be my charge per unit area times an area, whatever the element of area is. So I need to figure out what the element of area is for this little ring. Imagine I took a pair of scissors and I cut all the way around it, and I was able to straighten that out. What would be the length of that piece if I cut this all the way out and made it straight? What would be the length of it? Well, it would be the circumference of this circle. Its thickness is dr. Area is length times width. Notice if you integrate this with respect to r, you get pi r squared. And so this is going to be the charge per unit area we denote by the Greek letter sigma. And you put whatever sigma is. Sigma might depend on r, or it might be constant. So that's what your dq would look like. And your r squared would look just the same. The only thing about your r squared is instead of using a constant radius, it's got to change because you got to integrate over all the little rings that make up this disk. Okay. So the problem we did earlier is just a ring. The disk is the sum of those rings. So you have to integrate over r. The video I have on Canvas goes over this problem. You need to watch it. Okay. And then problem number 9, I have you go over how to calculate your dq's for various geometries. Now, the other one would be a three-dimensional object like a sphere. How would I break up a sphere that's uniformly charged, or its density depends on r? Well, first of all, the dq would be the charge per unit volume, rho, times dv. So if I have a sphere, how do I break up the sphere? Well, think of an onion. An onion has many layers. The surface area of each layer of the onion is 4 pi r squared, and the thickness is dr. And so that's the element of volume for a sphere. Again, we're assuming that rho is either constant or only depending on r. Otherwise, you have to do a double or triple integral. If you integrate this, you get 4/3 pi r cubed. Okay. So these are the various elements in 2 and 3 dimensions. And you might have seen this in Physics 205, but this is to help refresh your memory. And I think this is something that's good to see over and over again because students tend to struggle. Let me ask you guys a question. Oops, let me look at the chat. Are you allowed to do double and triple integrals if you felt like it? I mean, you could. It's less. I mean, I would say yeah. I'll say yes, but it's less physical. Be careful because you could easily make a mistake. Okay, I would just say that. Okay, and yeah, because somebody had 205 at least 4 or 5 months ago, you're probably going to have to remember that unit you did in 205 on gravity because it's the same calculations. Okay. And again, that worksheet, not that worksheet, but problem number 9 goes through these different ways of calculating your dq. And again, this is an important thing that you have to know how to calculate, okay? It's really important. Because you're going to have some version of one of these problems on the exam. Oh yeah, so I was going to ask you a question, I just forget. You learn in high school that density is mass over volume. And you learn that mass is density times volume. Is that always true? Yeah, it's only true if you have uniform density. Correct. Okay? This equation is only true if you have uniform density. So students learn this in high school, and then they think it's always true. But that's not always true. This is only true if this is constant over the volume. And we're going to be doing a problem where this is not constant over the volume. So really, M should be written this way. Or Q should be written this way. In this case, this is a mass density. This is a charge density. Okay? That you have to remember. And when you're doing these problems, think about the units, the dimensions of your integral. I don't know how many times people on a test will do this. This is charge per unit volume. And then you have a volume. So now you're going to have charge. If you integrate this, you end up having units of charge times distance. What is that? Okay. Don't do this. Okay. All right, don't do that. Okay, I want to do one more example. I want to do one that's very similar to the one I did the other day, except the charge density is not uniform. Again, that's going to help you to do problem number 9, the worksheet. Okay, so this next one, we have the rod again. And it's of length L. So let me draw the rod again. This is the rod we finished the other day. Except the one I did the other day, the charge density was uniform. This one is not. So its length is L. We want to determine the field at some point P, some location P, that's a distance A from the end of the rod. The charge density, lambda, is some constant lambda naught times x. But the total charge is Q. Since I know the total charge, I can actually solve for that if I wanted to, and I will. And that's going to be related to some homework problem number 9. Okay, so we have this rod. Oh yeah, I got to break it up into pieces. So let me break it up into, here's my dx, which is a distance x away from the origin. The r hat's going to be extremely easy for this one. Well, let's write our dq. Let's look at our dq for this problem. dq is equal to lambda dx. Right? This is the piece of my infinitesimal piece of the rod. Its length is dx. That dx times that charge density is going to give you my dq. And really, if I didn't know the charge, if I did not know that the total charge was q, then I would just leave it like that. But I know that if I were able to integrate this over the entire length of the rod, if I integrate dq over the entire length of the rod, that has to give me whatever this number is. Let's say it's 1 coulomb. Okay? If I know this number and I can evaluate this integral, then I can solve for lambda naught, because lambda naught is a constant. This integral is just L squared over 2. And so that means lambda naught is 2q over L squared. So that means then I can write the following. dq is 2q over L squared x dx. And if you notice, if I integrate this over the entire length of the rod, I end up with q, which is what you should get. Okay, so I have my dq. What's my r hat? R hat is the unit vector that goes from the source to the point. And that's in the I hat direction. All right, that vector points to the right. It's in the I hat direction. That was easy. I'm done with that. Now, what about R? Basically, I need to know this distance. It's the magnitude of the vector that represents this distance. Well, it's going to be this length minus this length. So it's going to be L plus A minus X. And so R squared is L plus A minus X squared. I have everything. I have R hat, I have R squared, and I have my dq. I'm going to put it all together now. My dE is going to be k dq, which is this. There's our r hat, and then our L squared. That's it. So that's the electric field due to an element of charge, okay, on this rod. If I want to find the total field, then I have to integrate over the whole rod. Okay? So let's integrate this over the length of the rod, and that'll give me the electric field. So I'm not going to spend time evaluating the integral. You can do this one by parts for fun. I'm just going to give you the answer if you don't mind. And here's the answer. Through the magic of Wolfram, don't tell your math instructor that, you get the answer, okay? Or actually, you can look up in a table. So that's the integral. That's the electric field. That's what it looks like. It's logarithmic. And again, you can integrate that by parts and get the answer. Question?
I have a question.
Yeah.
Professor. So what are the constants you can rip out for this particular integral? You can rip out the k, the dq, or the 2q L squared, right?
Yeah, you can pull all this stuff out.
Okay, just not the bottom though, because it has the x in it.
Yes.
Okay.
And so, so you have to actually, yeah, I would probably integrate that by parts. I mean, I guess you could try U sub too. But yeah, the only constant you can pull out is this. And it'll take you a while to do the integral. What if you're real far away? What if you're real far away from the rod? The rod's got to look like a point charge again. So let's look at what happens when you're really far away. Let's look at what happens when A is much, much bigger than L. Now, in order for me to look at this, I'm going to manipulate that equation a little bit. So let me rewrite it. I'm going to use one of the rules for logs. I'm going to write it the following way. Oops. Let me do one more thing with it. Okay, so I rewrote the electric field, and I want to let A be much, much bigger than L. We're really far away. It's supposed to look like a point charge. So what I'm going to do is, since this is the natural log of 1 plus some small number, I can expand this because the natural log of 1 plus x, where x is small, actually, I get that right? Yeah, when x actually doesn't have to be that small, is x minus x squared over 2 plus dot, dot, dot. And I'm going to only keep the expansion up to the first non-zero term. And so it turns out that when I do the expansion of this function here, the first non-zero term will be the x squared term. So I'm going to get 2, and x here is going to be L over A. So if I want to expand this, it's going to be x. X is over L over A minus 1/2 L over A squared. So this is approximately equal to. What does this give me? Well, the L over A's cancel. Forgot the I hat. And this is going to be something that's approximately equal to 2kq over L squared. The minus signs cancel. The 1/2 cancels with the 2. The L squares cancel. And it's going to give me kq over A squared I hat, which is the field due to a point charge. So it approaches the field due to a point charge when you're really far away. And that makes sense because when you're far away, that rod looks like a dot.
When you're expanding that natural log, is that a Taylor series, right?
Yes, you look it up.
Okay.
So physicists love doing these. Like doing, if they can do an approximation, then they will do it because they can make a really difficult calculation straightforward, and it will allow them to see the physics in the system. Physicists are known for doing what are called back of the envelope calculations or napkin calculations. Like they're sitting at lunchtime and they write on a napkin. They try to do a quick calculation. They do use these expansions because it can make a really difficult mathematical problem easy. And then even in the limits, it'll allow you to see the physics. Okay, so I've given you some examples of how to do these calculations, and I'm not saying this is going to be easy. The first time around when you're doing these are not that easy. You're only going to get good at it by practicing it. And it might not be enough just to do the homework problems. You want to find other problems in the book where you're calculating these. Okay, so it's an important skill that you have to have. By the way, you might be wondering, when I did the disc, or the ring, I only did the problems along the axis. You know why I did that? I only did them along the axis. It's because if you're off axis, you can still set up the integral off axis, but you will not be able to integrate it and get something, an analytical solution. You actually have to write a numerical, you have to do a numerical calculation. You have to do it on a computer using Simpson's rule or trapezoid rule to actually evaluate the integral. You won't be able to get an analytical solution, okay, if you're off axis. So I'm not going to give you on a test something that you can do, you can't do analytically. In other words, when you integrate a function, you should get some known function. Okay, that's the only kind of problems I can give you. All right, so now that we've know a little bit about calculating fields, let's talk a little bit about the dynamics of charged particles and static fields. Static meaning that the field doesn't change with time, time independent. So when I say a field is constant or static, I'm saying that the field is time independent. Okay? If I say the field is uniform, then I'm saying that the field has the same value everywhere in space. The uniform has to do with how it varies with the coordinates. Constant has to do with how it varies with time. Okay? So we're going to look at static fields. So suppose we have a charged particle in some sort of electric field. That's the only force acting on the particle. Then my free body diagram would be easy, right? It's either the field's going to point either, the force on the object is going to be either point in the direction of the field or opposite the direction of the field, depending on the sign of a charge Q. And if that's the only force acting on it, then I can apply Newton's second law. The force to the field is Q times E. That's equal to M times A. And so then A is Q E over M. Analogously, if we had a mass in a gravitational field, then we would set mg equals ma, and then A is mg over m, and the m's cancel. The only difference is that this m becomes a q. Notice we have the same form here, except that the two, you have an m that cancels here. There you don't. And if the field is uniform, if the gravitational field is uniform, then you have motion at constant acceleration. If you have the electric field uniform, then you have motion at constant acceleration. And the kinematic equations are easy, because you've done this before in physics 205. All right. Questions so far on this? And of course, we know that A is dV dt. all we got to do is integrate this. Actually, let me rewrite it. We're going to separate variables. I separate variables and then I integrate. That'll give me the velocity. As long as I know the initial velocity, I can find the velocity as a function of time. Same as what you did for kinematics. Our focus is mainly going to be on the case where E is constant and uniform. Motion of, same thing as a falling object in a gravitational field. And you will find that the method in which you solve the problem for a charged particle electric field is the same as a projectile problem. The only difference is the G is replaced by QE over M. That's the only difference. But for some reason, students have a hard time. Students have a hard time with these kind of problems. I don't know why. Because it's the same problem as technically it's the same problem as the Chapter 2 problems in Physics 205. Now, this field does work on a charged particle. And the work is defined as the integral of f dot dr, which is the integral of q e dot dr. And if E is uniform, then this integral is easy. Magnitude of the force times the magnitude of displacement times the cosine of the angle between the force and the displacement. Or you can write it like this. But according to the work kinetic energy theorem, this is 1/2 the mass times V final squared times minus V initial squared. The work done by the net force equals the change in kinetic energy of the object. And yeah, you have to remember this. And one of the homework problems has you go through this calculation for a charged particle in a uniform electric field. I also list in your notes there the mass of the electron and the mass of the proton, but we've talked about that already. Since the unit of joule is small for these kind of problems because electrons are light, protons are light, we introduced the electron volt. So a lot of times in problems in physics class, when we're looking at charged particle in an electric field, we write the energy of the particle or the change in kinetic energy or whatever energy we're calculating in terms of electron volts. We do that in physics. I think chemists, when they look at energy, they write it in terms of joules per mole. When we're looking at one particle, we're not looking at Avogadro's number of particles at any time. Okay? So things you have to remember. You have to remember the kinematic equations. You have to remember the work kinetic energy. You can't forget that. Okay? Let's say that the electric field is uniform. Okay, so assume uniform electric field. Let's look at this. So A is Q E over M, and V is the integral of Q E over M dt. If A is uniform, then this integral is easy. You're integrating a constant. You just get t out of it. Plus your constant of integration, which will end up being your initial velocity. But v is dx dt. And so if I find x, I got to integrate the velocity vector. I'm not, let me not say x, sorry. Let me call it r to be general. So let me integrate this. I'm integrating constants. What do these equations resemble? Did you study these in 205? The answer is yes, you did. This is motion to constant acceleration. So whether I talk about me taking a marker and throwing it across the room, or having a charged particle in a uniform electric field, problem is the same. There's no difference. The only thing is the way we write the letter A, right? In this case, A has a special form as QE over M. When we're throwing an object across the room, A has a form G. That's the only difference. Okay, really, that's it. So let me give you an example. Suppose I have an electric field that points downward and is uniform. I'm going to draw the arrows. So E points downward. So the same value in this region. And suppose I have a positively charged particle with some initial velocity v moving to the right. What happens when it enters the region where it has the electric field? What's going to happen to the particle? You tell me. Anybody? As this thing goes to the right, it experiences the field. What's going to happen to the particle? Is it going to go straight? Or is it going to curve?
Should follow that current, right?
It should fall down, right? It's going to do something like this. What shape is that trajectory? Well, the electric field's constant. The acceleration is constant. What's the shape of this function? What's the shape of the
quadratic?
Yes, it's a parabola. The trajectory is a parabola. That is no different than me tossing a marker across the room. That's no different. Whether I talk, granted, you can't see the electron moving, but you can conceptualize the fact that since the electric field is constant, it's the same problem as an object being thrown across the room because gravity is constant. It's motion to constant acceleration. Okay, for some reason, assigning a different letter here makes the problem different. It doesn't. The math is the same. It's a vector and the trajectory is parabolic, if the acceleration is constant. Okay, so this is motion at constant acceleration. We're assuming the electric field is uniform and constant. Now, if the electric field is not uniform, then the problem would be harder. I agree with that. But if the electric field is uniform and constant, this is no different than an object that's dropped in space. Okay? Let's do an example. It's a motion at constant acceleration problem. And basically, this is a plug and chug problem, by the way. So in this problem that you see on the screen, you have a charged particle in a uniform field. And let me write down some of the quantities. The mass is 1.2 times 10 to the 8th kilograms. Its charge is minus 1.0 millicoulomb. I hope that's not a problem with my symbols. I always forget that. The velocity is 3I minus 5J times 10 to the third meters per second. That's the initial velocity of this thing. The electric field is minus 6.00I plus 2.00J times 10 to the fourth newtons per coulomb. First question is, what is the acceleration of this thing? Well, A is Q E over M. So it's going to be 1 millicoulomb times the electric field divided by the mass. Of course, you do this on a calculator, and you will get 5I, and I'm not being careful with sig figs, minus 1.7J times 10 to the 7th meters per second squared. What is the velocity after 3 microseconds? I just use this equation. I know my A. I'm just going to plug numbers in. So let me use a different color. V is going to be V naught plus AT. So A is and we're doing 3 microseconds. You got to just punch this in on the calculator. And when you do that, you get doesn't change very much. 3.15I minus 5.05J times 10 to the third meters per second. Then it says, what is the displacement after 3 microseconds? It wants R minus R naught. Well, that's easy. I just got to plug numbers into the equation. It's a plug and chug problem. I'm going to have to erase here. So delta R is R minus R naught and v naught t plus 1/2 at squared. All right, so hopefully I have enough space here. V naught, you know what, I'm not going to put the dot at 0.00 because I know I'm going to run out of space. 3I minus 5j times 10 to the third times 3 microseconds plus 1/2 this acceleration times 3 microseconds squared. So when you work this out, you get 9.22 I hat minus 15.1 j hat times 10 to the minus 3 meters. That's the change in position. Okay? So I give you an example of how the kinematics and dynamics works for a charged particle in a field. And there's a couple of examples, a couple of problems you're going to be doing in the homework. And for some reason, these problems tend to notoriously give students a hard time. You just got to remember that these problems are the same as the kinematics problems you did in Physics 205. Okay, it's just that the source of the acceleration is different. That's the only thing you have to think about it, okay? If you think about it that way, then you'll understand that it's not that bad. So now what I'm going to do, unfortunately, I'm going to be saying some things that are a bit more abstract. And even though I'm going to be, over the next lecture and a half, saying some abstract things, it actually helps us to understand fields better. And so it's going to take a little getting used to in terms of the concepts I'm going to talk about the next lecture and a half. So let me start by talking about how we established the direction of the electric field. Right, I did that little thought experiment where I had a source charge, I placed it in space, and I brought a test charge in its vicinity. I determined the direction of the force on that test charge, divided by the test charge, and that gave me the direction of the electric field. By doing that, I can assign a unique vector at each location in space and time. And this unique vector characterizes the condition that that source charge produces when I put it in some location in space. In other words, if I take some charge, let's pretend my world is the whiteboard. Let's say I have a positively charged particle. I know the fields point away from a positively charged particle. So let's consider several points in space. Here, here, and here. At this location, I can define a vector that characterizes the electric field produced by that charge. I know it's going to be to the left. And I know this over here is going to be to the left, but it's going to be shorter because I'm further away. And this is going to be even shorter. These vectors uniquely define what the field would be at this location. So I can define a unique vector everywhere in space. I can do this over the entire board. Okay? That is by definition what a vector field is. And you would learn that in Calc 3. So I can define a unique vector everywhere in space that characterizes the condition this charge produces in space and time. So I can draw a picture, as you see in that slide. And those are electric field vectors assigned in space as a result of a positively charged particle. But I can connect those vector field lines. Let me rephrase that. I can connect those vectors to create something called a field line. So here's the example of the vectors that are assigned in space due to a positively charged particle. This is the vectors I would assign in space due to a dipole. And that picture is pretty good because the arrows, the size of the arrows indicate the size of the field. The direction of the arrows indicate the direction of the field you see in that slide. I can connect these vectors with tangent lines, and then what we end up doing is mapping the electric field produced by the source charge. We call these field lines or lines of force. So what I can do then is, and I only draw one set of them, I can connect these with lines tangent to these vectors. I can do it everywhere in space for this charge. And really, what I should do is draw them so that they they reflect the symmetry of this charge, but I haven't done that. I haven't done a good job of that in this picture. Maybe I'll draw one more here. That'll make it more symmetric. These now are the field lines that this produces. So what that means is if I put a positive test charge here, that positive test charge is going to move along that line. That's why they're called lines of force, because if I put a positive test charge on any one of these lines here, it's going to move in the direction of that line. So what I'm doing is mapping out, abstractly mapping out what the field is. Okay? Any positive charge I put on one of these field lines is going to move along that line in the direction of the field. So these are the field lines produced by a positive charge. So going back, this is the positive charge I had before. Now, these are the field lines for the positive charge. The yellow is the field lines. And you can see underneath it the vectors that are connected by the yellow tangent lines. And I can do the same thing for the dipole. What happened to my dipole? I don't have my dipole. I'll show one later. According to Michael Faraday, actually came up with this idea because he wanted to picture what a field line looked like, whether it was a magnetic field line, electric field line. Notice here that the electric field lines bunch up when you're real close to the source. And when you're really far away, they spread out. That's indicative of how strong the field is, right? Because the closer you are to the charge, the bigger the field is. And so the density of lines is indicative of the strength of the field. So if I were to draw an imaginary sphere here and another imaginary sphere way out here, both of those spheres have the same number of lines penetrating through it. However, the number of lines per unit area penetrating the small sphere is much higher than those penetrating the big sphere. That means that the electric field is higher on the smaller sphere, at the location of the smaller sphere, because you're closer to the charge. And so the number of lines per unit area that pass perpendicularly through the surface is proportional to the magnitude of the electric field. In other words, closely spaced field lines indicate large fields. When we draw these electric field lines, we want to draw them so that they leave a positive charge because the electric field points away from the positive charge, and they approach a negative charge because the electric fields point towards a negative charge. If you want to draw field lines to understand the electric field produced by a system of charges, you have to obey the following rules. First of all, the number of lines entering or leaving a charge is proportional to the charge. So for example, I drew these charges here. If I took another charge here and doubled it, if I drew 10 lines for this one, I'd have to draw 20 lines for this one. Why? Because I have twice the charge produces twice the field. And when I draw them, when I draw the field lines, I got to make sure they're symmetric. The field lines will either go away from a charge or towards a charge or go to infinity. That's how you draw them. And again, the density of lines is proportional to the magnetic field. The last thing about field lines that you have to remember, and it's very important, but people have a hard time with, is you can't have field lines that cross. Remember the electric field, with the electric field we assign a unique vector in every location in space. If two field lines cross, that means that I've assigned two different directions for the electric field at one location in space. That's not a field. That's not a vector field then. Okay? So here are a couple of examples, and after I show you the examples, I'll be done. I have the electric field due to the electric field lines due to two equal charges. What was done in this picture was to put two conductors in oil, and there were threads of string in the oil. When the conductors, the little dark dots, hold on a second. Let me blow this up. When they were charged with the same equal charge, same sign, notice that the strings, the threads, form lines. Those lines represent the field lines. Notice how they kind of repel each other in the middle, because they're equal charges. Now let's take a look at what happens with a dipole. Equal but opposite charges. That's what the field lines do to a dipole looks like. So this shows you the vectors that are connected by lines. Remember the vectors I showed you a little while ago? These are the vectors connected by lines. Let me show you this video. I'm going to have to, when I put this on YouTube, I'm going to have to blur this out because of copyright.
To the ground attachment of a Van de Graaff generator, we connect a large conducting sphere. When we turn the generator on, the generator's sphere becomes strongly positive in charge, and the other becomes strongly negative. We sprinkle bits of fur into the air around the spheres. A very distinct, stable pattern appears. This pattern indicates an electric field. Notice that the field is not quite symmetrical. This is caused by the presence of other conductors, such as people, in the vicinity of the spheres.
Okay, that kind of shows you another example of field lines. So I did...
To the ground attachment of a Van de Graaff
So I'm done discussing. I'm not going to talk anymore, and I thank you for staying a little bit over. This material on field line is chapter 24, for those of you who are asking about it, okay? So what I'm doing right now is chapter 24. I'm done with 23. Okay, this material, they kind of related to each other, but just one second. So yeah, this is what we're doing right now is chapter 24. So we completely finished chapter 23 already. Any questions? or concerns? I know I am on campus today, but I'm kind of unavailable after this class because I have meetings after this. Okay, so if you have a question, please email me. Okay? I have two, or you can ask me right now.
Yeah, I do have a quick question.
Okay.
For the chapter 27 homework, it was originally due before the chapter 23 homework.
Yeah.
Do we have to read chapter 27 before we read chapter 23?
No, I sent you guys an email last week because somebody asked the question. I would read and I would scan through chapter 27 for Friday. It's not a long chapter, and it's not really a super difficult chapter. I'm going to talk about chapter 27 on Friday, so we can talk about the multimeter quiz. And I know we're kind of going kind of quick on the labs, but it's just the structure of the course this semester. I apologize for that. But before Friday, if you can scan through chapter 27, that would be great. And then there's a homework assignment due after that. I think I put it the 24th. It's in the email that I sent you. When I change a homework deadline on WebAssign, it won't show up on Canvas. You have to actually look in the WebAssign. Does that make sense?
Yeah, it does. Thank you.
Okay. All right. So I'll either see you tomorrow in student help hours, or I'll see you on Friday. Okay?